Okay, so not many people are here, but we'll get started anyways. Those that didn't come, hopefully they watch the video because they're going to be really confused. So today we're going to have an exam on Tuesday, so I guess that's a week from today. And we'll hold a review on Thursday. So this material won't be on that exam, but I wanted to start getting it introduced because it's kind of a complex. Oh, look, everyone's trickling in. All right, cool. So we've kind of run into, I guess everyone had to scrape the ice off their windshields or something today. Is that what happened? So what we're going to be talking about is called state machines. And state machines are the next step in our digital design. So what a state machine, well, first off, what we've designed we would call the data path, right? It's how do we control and manipulate data. The next part of it is controller. So the two concepts, data path and controller. We're moving on to controller. And this is where we've been going with the flip-flops and memory, circuits with memory, right? Is that we need to be able to remember what's happened before to decide what happens next. And so a state machine is something that is very common in all sorts of design, including more traditional programming languages, but certainly is everywhere when you get into designing digital logic. And what a state machine is it essentially is looking at what are our inputs, what state are we in now, and based on the inputs, where we are, where do we go next? Now, the description may not seem clear, but it's an easy concept once we give an example. Let's take a stop light. Let's call red our beginning state. We start at red, right? And I'm going to, while I kind of walk through this, introduce what we call state diagrams. So what we want is, let's start at a red light, right? It's just sitting there. Now, we want to go to green, right? Eventually. I'm just going to write G for green. Then we're going to go to yellow. And then we go back to red, right? Those are our three states, written from the perspective of the output, right? And we'll get into some more traditional state machine diagram. And now, what does it mean, this arrow? What does the arrow mean? Why do we transition to green? Well, we might have some sort of input, right? We have lots of different ways that we provide input. Sometimes it's just a simple timer. Sometimes it's like a pressure plate. Sometimes it's a radar system, something that tells it a car is there, right? So let's say I have input C, input car. So our input is C for car, meaning that if C is asserted, that means whatever sensor we're using to detect if a car is there at the stoplight, we want to go green. Well, we need one other input, right, to make sure that the other direction isn't green, right? Because you don't want to turn your direction green if the other one is. Okay, so second input is car, and I'm going to use D just for the other direction. Okay, and in fact, I'm going to say not D. The other direction isn't green. Okay, so what I would write then is essentially this transition happens if car and not D, right? This is a logical operation. And then this is our input list. Then we do a slash, and we can have an output list. Now, there are two types of state machines that I'll delve into in a little bit. And one of them I've already drawn with this example, where our output happens when we're in a state. The output only cares about, or the output only depends on what state we're in. as opposed to what state we're in and what the inputs are at a given time. And I'll draw these two comparisons. So this being our output is based on what our state we're in. Where are we right now? What is our controller doing and waiting for? Well, we're in red and we're waiting for car and not the other direction. Okay, so the other direction goes red. So we have we pull up, the other direction goes red, we can now go green. Now we're gonna stay green for, I don't know, some amount of time, right? And so I'll just call that T for timer. T timer. So it's just after some time. And again, I'll do that on yellow, T timer. So this is what is called a non-proper or an improper state machine, because I haven't declared all possibilities, right? I haven't said what happens if I don't have this. So what I do, if I wanted to be proper, is I would just draw a circle that says stay in that state if this isn't true, right? And so this is basically saying, well, every other combination of this. So you could just say not. Right? And then you could go through each of these, and really you could list, sometimes they'll ask you to list all possible inputs. So here I'm using timer, but we still have C and D. And here we're using C and D, but don't have a timer. So if I wanted to do it ordered as CD timer, and I wanted to be fully explicit in what my possible decisions are, it would be CD don't care. And similarly, this would be don't care timer. Right, that's like the fully kind of written out all of the inputs. And then this is just not timer, right? And everything else is don't care. Okay. So that's all the state machine is doing, is we're looking at what is our system trying to achieve and creating memory that remembers where we are now and creating logic that determines when we go there next. Okay, so I'm going to go ahead and pull just a simpler kind of arbitrary type of state machine that has only one input and one output so that we can kind of build up some more complicated ideas in this. So one of the important things with state machines is it has memory and it is clocked. It must be clocked. And what you do by default is each time you have the rising edge of the clock, or falling edge if it was falling edge triggered, right? But if I have a rising edge of a clock, then I want to evaluate what are the inputs at that rising edge. So the clock's going to be ticking along. And each time a rising edge happens, we're going to go look at the inputs and see what do we do. Okay, that's what the state machine is representing, is each arrow is a decision at the clock. So in the case of the timer, it would have looked something like, for a long time, there's a timer that is counting up, counting up, counting up, counting up, and then it asserts for some amount of time that says, hey, my time is up, go ahead and move on to the next thing. That's just kind of how timers work. In this state machine that I'm about to build, we're just going to step through at every rising edge of the clock. So let's call these just states A, B, and C. So those are my states, and they're going to transition as follows. So I'm going to do this as the other kind of state machine, which is, so the first one was called a more state machine, which I'll come back around to that. And this one is called a melee. So this one, the mealy state machine, it doesn't just care, its outputs don't care only about what state we're in, they care about two things. What state are we in, and what is the input? So the way we write this, again, is similar to what I kind of started alluding to, where I have, if my input is 1, okay, actually, let me rephrase this. If I'm in state A and a rising edge of the clock happens, if my input is 1, then I'm going to move to state B, but my output's going to be 0. So input, output. A 1 says I move, a 0 says the 0 is the output, don't assert the output. If I want to stay here, right, otherwise, if I get a 0 as my input, I want to assert my output. I'm going to erase this. So now, if I'm in state B, if I see a 0, still 0, stay there. However, if I'm in state B, I'm going to go back to state A if I get a 1, and I'm going to output a 1. Okay, similarly, if I'm in C, I'm going to go back to B if I see a 0, I'm going to output a 0. But if I'm in C and I see a 1, I'm going to output here and assert a 0. So you'll notice something. The only time that this is outputting a 1 is if I'm going or in state A and I see a 1. So basically this is checking for 1s without long strings of 0s, more or less. So let's discuss kind of what's happening here. So each clock period, the input is going to see an input. So here's a clock. And let's say that it has a stream of inputs coming in, and I'm going to offset the input bits by just a little bit, by half a clock period, so it's easy to draw or easy to see. So we're going to go ahead and give it a 1, 0. That's actually probably a better spot to do it. So 1, 0, 0, 0. And then I want to do 1. And now let's see what happens to this state if this is our input. Well, oftentimes we'll write an arrow like this that says start. That indicates where does the state machine begin, right? In the case of like stoplights, it makes sense to start at red, right? All stoplights start at red. Here we're going to have this A. A lot of times you'll call the start state idle, waiting for some input to move it out of it. Okay, so I say if I started in A and I get a 1, I move to B. So I'll write this clock input state. Okay, now I'm in state B and I'm moving to state C because I got another 0, right? My input is 0, I'm in state B. That means go to state C. Now I'm in state C, I see another 0, so I move to state B. I'm in state B. Oh, this is where I wanted my 1. So I can illustrate this, sorry. In state B, rising edge of the clock happens, sees a 1. That means I go back to state A, and there I am. Now my output, let's start off saying I don't know. Well, B, no matter what or if my output is 0, sorry, if I'm in state B, my input is 0, my output is 0. C, no matter what, my output is 0. I've moved back to B. I see a 1 here. So there's a couple different ways that we could design this logic. One of them is we don't update the output until the rising edge of the clock. And one of them is we update as soon as the input changes. We can do it either way. Either way is fine. I'm going to stick to update at the rising. Well, no, I'm going to start here because this makes a lot of sense. So the input changes and it goes high because B, this an immediate state machine, cares about both what state we're in and what the inputs are, both the state and the inputs. So it goes high because the input goes high. Again, you can delay that until the clock ends, either way it's fine, but I want to illustrate this. So now we've got a 1, and we go back to A. So if we're in A, it would immediately drop back to 0. Oh, wait, sorry. This is the input. I've got to do the output. Because in state A, if the input is 1, my output is 0. Right? And that's if I have just strictly combinational output that has the input and current state logic. So the other way is we don't update it, and I'll just do this next line, where we don't update till here, and we have one whole clock period that happens where last time we were at B, our input changed for one clock period until wherever the next clock happens. I'm going to keep what that output was. Either one of those can work. And you need to be aware of which one's happening, because if you don't, if you're not careful, then you'll notice that this doesn't really happen at this rising edge of a clock. So if you had some synchronous circuit that is waiting for the output of this to be true, to be 1, it could miss it depending on what the gate relays are. So you kind of want a little bit of extra time to hold it true so that you don't actually miss the asserted signal in between two rising edges of clocks. Okay. So you can also have, right, I mentioned, well, actually, I'll skip this one. Another way to describe state machines. This is a state diagram. We could also have a state table. And we often start with a state diagram because this is a good way to picture what the system is supposed to be doing. How is that controller behaving, right? And so you could think quickly, just another example is like your washing machine, right? It has a controller in it that is controlled by a state machine. And your washing machine is just, what is the input, right? Turn it into wash, and it's going to have that timer. And when it hits the time, the certain amount of time or the position, however they want to measure it, then it'll change from wash to rinse to dry, right? More or less, that's a state machine. And the outputs change when you're in those states, like fill it with water. And the next is spin it around, right? And then drain it, and so on and so forth. State machines are everywhere. They control almost everything you kind of interact with that does more than one thing. It's a good way of phrasing that. I don't know. I'll think about a better way of phrasing that, but basically you run into state machines constantly. Okay. State table. Yeah, I'm going to use the state table for this diagram. And we have a couple of concepts. So we have the current state. Where are we now? Well, our choices for current state are just A, B, and C. We also have next state. Now, the next state is a little bit different because the next state cares about what is our input, right? So if we call our input W and our output, well, I'll deal with that in just a second. So we're going to call our input W. So our next state depends upon what is W. So we can fill this out, right? So if I'm in state A and W is 0, I stay in A. But if W is 1, I go to B. Okay, similarly, B, if I'm currently in B and W is 0, I go to C, otherwise I go to A. If I'm in C and I get a 1, sorry, I'll start with the 0. If I get a 0, I go to B, otherwise stay in C. Now the next thing in my table is what is the output doing? And I'm going to call the output Z. And again, in this case, the output cares about what the input is. All right, and now we would just go through and fill it. Well, if I'm in state A and I get a 0, I get a 1. And there's only one other spot that I get a 1, so I can simplify this out, right? Is if I'm in B and I get a 1. In B, W is 1, I get a 1. Otherwise, there. So that's all a state table is doing. So the state tables are just another way of describing the state diagrams that are a little bit more friendly to design optimization. The state diagram is a little bit more friendly to human understanding and human thought processes. It's not as clear looking at this, but you can easily bounce back and forth between the two as long as you understand what they're doing. And it's likely on an exam, I would give you one or the other and ask you to derive the other one. Or I'll give you a word problem, and this will be on the final, obviously. I'll give you a word problem that asks something like, given this information, build me a state diagram and state table. Okay. Let's go ahead and do an example. I'm going to leave the state table up. I'm going to do a different. Okay. So let's say we have a very simple state machine that is just going to be an adder. It's just going to add numbers. But instead of doing it all in parallel, it's just going to go bit by bit, kind of like we would if we were going through and doing the arithmetic. So I have state 0 and state 1. Those are the only two states I need. And if I have an input of 1, 1, let me just draw this out. Okay, so those are our transitions, and then we stay in state 0 in everything else, but we need to worry about adding 2 numbers. So I have 2 inputs, right? Because this is a 1-bit adder. And then we have an output that is 1 bit. Okay, so in the case that I have a 0, 1, then I get an output of 1, right? Because 0 plus 1 is 1. Similarly, if I get a 1, 0, I get a 1. If I get a 0, 0, I get 0. The special case happens in 1, 1, right? Because that's where the carry out happens. And so you want to have kind of a special case here that we stay in. Otherwise. And it's just taking the opportunity that if I get a 1, 1, right, then I now have a carry. So I go to this state that is dealing with having that carry. And now if I have a carry and add 0 and 1 with the carry, right, or the carry sitting over here, then I get 0 with the carry as I go back. That's all this state is doing, is it has the special case of there's an extra bit intrinsic to the S1 that it's adding in addition to whatever the 2 inputs are. Does everyone follow that? Okay, so that's all our 2 states. That's all we need in order to make an adder. And each clock period, we're going to synchronize the inputs, and we're just going to give it, we could give it some n-bit number. Let's say it has inputs X and Y, and X could be something like that, right? And it's going to take these 2 numbers, add them together. And actually in this case, I'm going to do a 1 here because it's a little bit more illustrative. It's going to add them and output a 1. So I have some serial register waiting to be loaded, like a shift register, like what I talked about, right? It's going to go, oh, 1 and 0 are inputs. Let's shift in a 1. That's my result. The next clock period, it's going to go to the middle section and say, well, 1 and 1, let's shift in a 0 and go to state 1. That's what that says. And then I'm here in state 1, and I get a 0 and 1. 0 and 1, it outputs a 0 and goes back to state 0. So it's just going to continually sit and add 2 bits of those 2 vectors. 1 bit of each of the vectors, really, right? So this is a state machine that is going to slowly add things together. Then, once again, we can take this information and turn it into a state table. I regret erasing this, I'm pretty sure, but. Okay, we do the same type of thing. We say, what is our current state? What's our next state going to be based on our inputs? And what is our output? Now, the next state gets a little bit more complicated because I don't just have 1 input, right? I have 2 bits of input. So I have to fill that out for all possible input combinations. So I have to do something like not X, not Y, not X, Y, X, not Y, and X, Y. Those are all my possible input combinations. So my state is pretty easy, right? Because I can only be in S0 or S1. And then I just have to look, where is the situation for S0 that I don't stay in S0? Well, it's 1, 1. So I just say, well, here I go to S1. All the others, I stay in S state 0. Right? All combinations stay in state 0, except for 1, 1, go to state 1. Okay, same thing is true for state 1, is my only leave condition is 0, 0. Otherwise, stay put. Make sense to everyone? Yeah.
So how do you actually get back from, so our S1 is when we're essentially our math with a carry in. However, shouldn't we also, like in the example, we have kind of where we're adding a carry in, but there's not going to be a carry in for the next line. So why are we still in that state?
Yeah, so if there's not a carry in, well, let's walk through it. 1, 0 stays. 1, 1, we go to state 1. We have a carry, and now we've got 0, 1, which is 0 with a carry. So I'm still there. Eventually, I will get 0 without a carry. And then, yeah, 0 without a carry sends me back to state 0. That's the only situation that I've lost the carry. Good question, though. Okay, now our output, we have to do the same thing because it relies upon both the inputs and current state. And then we would just fill in, what is the output doing? Well, we're pretty complicated, actually. I don't see a simple way of doing this. If I'm 0, 1 or 1, 0, I get a 1. If I'm 0, 0, I get a 0. And if I'm 1, 1, I get a 0. All right. If I'm in state 1, I get 0, 0 is a 1. And also 1, 1 is a 1. Otherwise, 0. Okay, so that's the state table describing our adder. Our serial adder is what it would be called, right? Because it's adding one bit at a time serially. Okay. Now, let's say I want to build the first state machine as a more state machine. So in general, so I'm going to say this again because it's an important concept. More state machines their outputs rely only upon what state they're currently in. Their current state determines the output. Mealy state machines the output is determined by both the current state and the inputs. Now they're drawn differently. In general, it's easy to know something about a Moore state machine because a Moore state machine usually requires more states. So they're spelled differently. The state machine is 2 O's. And then the Mealy state machine is like so, Moore and Mealy. I see that. So building up that simple state machine, a Moore state machine will look something like this. Okay. So now the outputs are easy because it's just saying if I'm in A, my output is 1. If I'm in B, my output is 0. And if I'm in C, my output is 0. Right? This is the same state machine that I described there. It's just it depends only on the state. So the output in this case cannot update until we're back in state A. And it will always stay high for one whole clock period. Right? So the clock period happens, it says, oh, it's 1, move to B. Next clock rising edge, it's a 0, move to C. Next clock edge, if it's a 0, back to B. Next clock edge, if it's a 1, back to A, and then make it true, assert the input. And if it stays, and if it then goes to 0, we would just stay in A and keep asserting, right? The output is only dependent upon which state we're in right then. This is a Moore implementation. Now, I've kind of started alluding to this, but you can, instead of writing like 1s and 0s, you can write them as the signal. So I said the input is W, right? So instead of saying 0, I can say not W. And then instead of saying the output, so if the output is here, right, I would say the output is Z, I said. Right, and now I'm talking about the state machine in terms of its input and output names. Now it's the same thing, right? It's just a little bit more visually descriptive of what are the variable names that I'm inputting or outputting. And the nice thing is you can start tacking on other outputs, right? Saying Y and Z or whatever you want. Similarly, if you were doing the Mealy state machine, right, you could do not W slash, so input slash output. The output I said was Z, right? Something like that. If it was a Mealy instead of the Moore drawing. So that's just one way of drawing the visualization of that state machine. And for the note takers, interpreters, I'm going to skip over this number 6 for just a minute. We'll come back to it. And I'm going to go on to 7. Okay. So similar to how in our, and you're going to see where this is going, I hope, in our project 1, we set up opcodes, right? And I had you write something like constant add op, and it gets assigned to, right? You assigned your operational code, and you needed 3 bits because there were more than 2 to the 2-bit selections, right? There were 5 different opcodes, so you needed 3 bits to encompass all of them. State machines have the same idea. We're assigning a state number, right? A state identity, because we can't tie it to a name in binary, we tie it to a number. So our state A isn't A. I don't write A. Instead, I write, well, I could write something like this. Constant A is, I only need 2 bits, right? Because I only have 3 states, is 0, 0. So I'm just choosing what is that state's number. Well, it's state 0, so state 0, 0. We have to do that same kind of idea, just like we did with the opcodes. And you're going to notice, hopefully, you might have some intuition that that's where we're going with this ALU, right? That's what's coming up in the next project, is we're going to start using state machines to control a series of commands. Okay. So there are a couple of rules that it comes when we start assigning states. We are saying, what is our state number? Well, the 3 rules that we really care about are, I don't want to write these. I'm going to say these down, let you guys write them. Okay, first one. If states have a common next state, their number should be adjacent. So if there are 2 states and they both end up at the same spot, this is a good way of doing this. So both A and B go to C. A and B should have adjacent numbers. Similarly, if you have the other thing happen, if there are 2 states that can possibly come from a common previous state, those 2 states should have adjacent number assignments. And then lastly, the third rule is if a state has the same output, given the same inputs, they should be adjacent if possible. Something like this. So if the inputs are 0, 1 for both of them, they both output 1. Otherwise, they stay in output 0. G and H should be adjacent. Even though they're not linked to each other, we want them to be the same. Now, it's a little outside the scope probably of what we're going to cover in this class as to why, but it has to do with the combinational logic that determines the next state. Is we're minimizing the probability of accidentally ending up in an erroneous state. And that'll make a little bit more sense when I get to drawing what the circuit of a state machine looks like, which we're about to do. Okay. So there are three main components to a all state machines. The first is the state register, which is the memory that remembers what state are we in now. The next part is the next state decoder. That's combinational logic that takes the input and the current state and determines what is the next state supposed to be. The third part is the output decoder. This is also combinational logic that takes what state are we in, what are the inputs, and outputs the output if it's true. So I'll say those again: the current state register, the next state decoder, and the output decoder. Those are your three main parts. And we'll delve into each of those because a lot of the times when we start writing the VHDL of a state machine, we'll combine multiple of those three elements into one thing. But for now, let's just go ahead and draw what does a state machine actually look like in logic, because this can really help. So I'm going to call this R. This is our state register. This is where our current state is stored. And it has an output of n bits, however many bits we need to store all of our states, right? That is called, we're going to call it Q. That is our current state. Q is our current state. Well, we can have, and call this OD, the output decoder. That considers, well, what is Q? It also needs to consider what is the input. Now, this up here is only existing if you're a Mealy machine, right? Because on a Moore machine, I don't care what the input is for the output decoder. I only care what the current state, Q, is. So this path, this data path, is optional. Now next, I have the next state decoder. That does always, so I'll dash this so it's a little obvious. So that line is optional, right? The solid line is not. It always cares about the input. Now, the other one that we need to worry about is the current state does feed back around into the next state decoder, because I can't decide what my next state is unless I know where I am. And then you'll usually have, right, a clock. And then you might have something like a reset pin or something. But the clock only needs to go to the next state decoder informs R. Yeah. So the clock only needs to go to the current state register. That's the only clocked component of this. Everything else is just combinational logic like we've dealt with before. Okay. I'm going to shrink this line just a little bit to give myself a little more room. Now, what is our output decoder logic, or what is our next state decoder logic? Well, the output logic is pretty easy. So we know that our states have to be stored in bits. So we might assign something like that, right? And actually the example I have does this, where 1, 0, and I'll just squeeze it in here. And I'm just gonna throw in and call it delta. And it just doesn't care. It should never get to that state, right? So it's a don't care state. But it exists, right? Because there are 4 bits. I have to have 4 states. It's just one of them, hopefully I never end up in it. Okay. Now, how do we design then the output? Well, it's a K-map, unsurprisingly perhaps. And it's a K-map that has 3 bits. Does anyone know what those 3 bits are? What are 3 input bits to our output decoder? Up there, what are my 3 bits? Yeah, so 2 of them come from Q. And 1 of them comes from W. Right? Q is a vector. It has to be in order for me to have enough bits to represent all 4 states. Well, I already said, let me fill this out. Right? And so you're starting to see, I hope, how everything that we started out with is kind of building on itself. Right? We've had this K-map since early on in the semester, and it's still important. Okay. Now I said in the case of if my Q is 1, 0, I just don't care what my output's doing, right? I don't care. Other than that, I can just go in and start filling it in. Well, if it's 0, 0, 0, I get a 1. If I'm 0, 0, 1, right? So 0, 0, 1. 0, 1, 0. 0, 1, 0. 0, 1, 1. And then lastly is the 1, 1s are both 0. So now I've just filled in a K-map using the bits that I need of my next state decoder and the input, because that's what my output cares on. If I didn't have a Mealy state machine, I wouldn't need W, right? I would just have the state. It's easier to design the output decoder logic. Then we could go ahead and do our K-map, right? Which is this, where we end up with saying, so this whole thing was for Z is equal to, right? I said Z, yep, Z is equal to, well, W doesn't change, and Q0 doesn't change. Yeah, and it's not both of those. Or, well, all of them 0, 1, that, so W, Q1, Q0, and it's 0, 1, 1. Sorry, I did this backwards. W is 1. Q1 is 0. There we go. Right? So now I've used my K-map to determine what is my output decoder logic. And I can turn this into a circuit, right? Really easy. So that logic, that circuit is what plugs into output decoder in the case of this state table. Does everyone follow that design process so far? Do you have any questions on that? Okay, now let's do the next state decoder. I'm going to do that here. Okay. And the next state decoder is much like the output decoder in that it is going to have 3 possible inputs. It has a W and Q1 and Q0. And it's just, instead of using this column of the table, which for the video they can't see, instead of using the Z column of the table, it's using the next state column of the table. Okay, so what is the next state doing? Well, what it says, I probably just need to try and make this fit. 1 second. Or video people are getting very confused if I don't. Okay, so yeah, so video people, we're going to be using this next state. Now, what we have to recognize is it's the same one, Q0W, that I actually need 2 of these tables. Can somebody tell me why I need 2 K-maps?
Because A, B, and C are 2 bits.
Exactly, because A, B, and C are both 2 bits. So we have one that is, and if I don't call this Q, because Q is the input, so the output, I could like do Q positive or something like that, right? That would be an OK notation. I'm going to call it D. So the next state, what comes next, what gets updated into the register on the rising edge of the clock is called D. And D, just like Q, must have 2 bits. Now, those 2 bits are encoded in this next state table, right? Where A is 0, 0, B is 0, 1, C is 1, 1. Should probably use a different color for that, sorry, but right. So those are just the state codes. And then when I start writing it, I only care about 1 bit at a time. Okay, so let's do P0 and start if I'm in Okay, let's worry about D0 and let's start with A. So if my current state is 0, 0, and W is 0. So we're 0, 0, 0. Then my next state, first bit, is 0, right? And so what's going to happen is it's 0, 0, 0, 0, 0, 1. 0, 1, 0, 0, 1, 1, right? Everyone kind of follow that, so I can just do 1, 0, don't care, 1, 1. Okay, yeah, that matches my notes, so optimistic. Does everyone see what I did? Is I just plugged in all of the orange underlined numbers into their corresponding. So going, I guess just listen up. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Don't care is 5, 6, 7, 8. Right? And then I can do the same thing for the most significant bit, the MSB, the larger bit, which is just going to be 0, 0, 1, 0, don't care, 0, 1. Zero, 1. And then I can do these K-maps. Write expressions for that. And I can then plug in the next state logic, right? And make those circuits. So now you can kind of visualize what the bubbles are, the NSD and the OD logic looks like based on these logic equations. Right? And I'll probably bring it up in a later lecture, but I want to give you a kind of a flash ahead so we know where we're going. This is kind of why we started talking about the setup time, the hold time, and the clock to Q time. Because those determine how fast this state machine can run, right? Because if a clock hits, rising edge of a clock, there's a clock to Q delay for D to put onto Q, the next state to get loaded into current state, right? So that's clock to Q delay. Then that feedback comes back around and goes through the next state delay. If this delay is really long, then we could have a problem if the clock is fast, right? Because we need to get D ready before the next clock happens. How long does it take D to get ready before the next clock happens? Well, that's tied directly to how complicated is this logic up here, right? And if you're not ready and that clock happens early, you could end up in this don't care state, right? So let's say one bit has a longer delay than the other. And let's say we're going from state B to C. Is that gonna, well, actually, this is a good design. B to C can actually run into a problem. But if you had a way from going from A to C, right? And this is why those 3 rules actually come into play, is they help minimize this risk. But if you had the possibility of going from A to C, and one bit was a less delay than the other one, then maybe Q1 switches. Q0 hasn't switched yet, but then the clock happens and we end up in don't care land. That means we don't know, we have no idea what's going to happen next on the clock. It could stay in don't care land, or it could end up back in a normal state and everything's fine. Generally, that doesn't happen very much to modern designers. If you're using VHDL, VHDL tools are really good at avoiding that. But some of that's kind of like 3610, your junior level next follow-on course to this material. Okay. So then we have these equations that I should probably solve, right? So this one is only going to have one variable, and it's D0 is equal to Q1. And D1 is equal to Q1 W or zero, 1, 0, something like that. And then we just go ahead and start plugging these equations into those circuits. Right? That's the output decoder logic. And we can go ahead and design the rest of that. So I'm taking you through essentially the entire design of a state machine of how you would make that. We're going to be doing that in homework assignments and in a project and in a lab. So we're going to be doing a lot of this. And in fact, state machines are 90% of the remainder of the semester. I've left a fair amount of time to kind of talk about these, give some slow time, and then we'll actually spend some time in class instead of the projects. I'm seeing how this goes. I didn't do it this way. We didn't get to state machines quite this fast in my last semester that I taught this. So we'll see how this goes. That's 5 minutes early. I'll call it quits, let you guys kind of digest some of this material. We'll plan on having an exam review on Wednesday Thursday. Between now and then, and certainly before the weekend is my target. I'm going to start posting the exam, or not the exam, the homework solutions for the homeworks that you guys have done since the last exam. Now, I don't want you to think that like, oh, there's only those homeworks, right? But because I can still ask K-map questions. I can still ask, I probably won't, but I could ask like digital logic simplification. If I do that, I don't expect you to use Boolean algebra, right? Even if I phrase the question as Boolean algebra, right, you can use K-maps. Use the tools you know. For this class, the whole idea is that we're kind of building on more and more complicated ideas. So as long as you kind of understand the homeworks, you should be good. And I'll start posting the homework solutions so that you can use those to study. If you have any questions, you can go ahead and ask. I'll hang out for a little while. And then I have office hours immediately after this. Well, starting at 10:30. So I have a little 15-minute break, but then